Well, hello there. Welcome to this video. This is Dr. Dell speaking, and the title of this video is What is Math? Now, that's really aimed at anybody that is really interested in just what is math? What's it all about? Maybe you're even thinking of studying math at a deeper level, or maybe even thinking of becoming a mathematician. Then this is what I think you need to know. Now, one question that's often asked is math something that's discovered, or is it something that is invented? And my answer to that is it's both of those things. And here's why. Mathematics, consists of a collection of what we call axiomatic systems. And these are invented by sapiens, that's you and me, Homo sapiens. Okay, what is an axiomatic system? You have to understand that to understand what math is. Well, an axiomatic system starts out with a set of what are called undefined terms. These are usually symbols. And of course we invent them. We say, okay, here's a set of undefined terms. Now, by undefined, that means that they have no intrinsic meaning until we give them some with what are called axioms. And I'll tell you what that is in a minute. Now, the meaning to these undefined terms, if you want to call it that, is given by the axioms and by nothing else. So, for example, in geometry, the undefined terms might include point and line. But that doesn't have any meaning until you tell about the relation between them and how they behave. Now, I will tell you this, that when you apply mathematics, you then give what are called ostensive definitions to these undefined terms. So if you're going to apply geometry to something that we do in real life, then you know what a point is. And a ostensive definition is how you first learn a language. That's what children learn. If I say, what's a cat? You point to cats. Pretty soon a child knows what a cat is. At some level they know. You don't give them a complex definition of a cat. You just point to a cat. You point to a dog. They see the difference. Later on they may learn a lot more about them, but that's an ostensive definition. Then, of course, we have defined terms, and these are simply new terms that we create and derive from the undefined terms. So, for example, in geometry, triangle would be then a new defined term, but we defined it in terms of the undefined terms. In other words, a triangle consists of three straight lines connected, or what is a circle. These are defined terms. So that's how we start out. We start out with a set of undefined terms and some defined terms that we invent. And then we want to say how they're related. So axioms, the word axiom means an assumption. And it's an assumption about the relationships of these undefined terms to each other. So for example, in geometry, we might say two distinct points determine a line segment, which is the set of the points in between the distinct points. In other words, we have relations between them. If you go look up Euclid's elements, you'll see the axioms. Sometimes these assumptions are called postulates. Axiom and postulate means the same thing. And Euclidean geometry was the first one that we actually did this with. Way back, the Greeks did it. They set out with a set of undefined terms, and they basically then defined them, if you want to say that, with their axioms and their postulates. Now, once you've done that, you can then write down meaningful statements. And these meaningful statements are things that you create or invent, and you write them down. And or you could say you've discovered a meaningful statement within this axiomatic system. So the statement is all about these undefined and defined terms, and it has to be put together in a logical way that's meaningful to you. Now, a meaningful statement has the following property in math. It can either be true or it can be false, nothing in between, 0 or 1. Math is based on what I call bipolar logic. A statement is either true or it's false. There's no in between. And that's a big characteristic of mathematics, and this is something that started way back with our ancestors, the Greeks. Now, once you've got your undefined terms and your axioms, and then some meaningful statements, a meaningful statement might be true or it might be false. So a theorem is a meaningful statement that you can actually prove that it's true with a finite sequence of logical statements, deductions. It's called a proof. So you start out and you just sort of start out, and one statement logically leads to a second statement. And that logically leads to a third statement. And that continues on till you finally get to the meaningful statement you're trying to prove, and they call that a theorem. Sometimes, by the way, they use the word lemma, L-E-M-M-A. That also means theorem. So that's what math consists of. It's a set of undefined terms and defined terms based on them, axioms, which are assumptions, those are invented, and theorems, which you then discover, meaningful statements that you can prove are true with some logical deduction. That's all a mathematical system is. A great mathematician once said, a mathematician is someone who knows a great deal about nothing, meaning the undefined terms, well, what are they? Well, from a mathematics viewpoint, they're nothing. Now, from a science viewpoint, you give them meaning with extensive definition. That's why mathematics becomes very useful in science, and I'll talk about that in a moment for the creating of math models to model science. Now, here's something that you need to understand. An axiomatic system is considered to be consistent if you cannot prove a meaningful statement and its negative statement, like A and not A. That would be a contradiction. If you could prove A is true and you could prove that not A is true, that's a contradiction. And then that means from that you can prove anything is true. So that would be of no value. So an axiomatic system is consistent if you cannot prove a meaningful statement A. Now, if you have a complicated system, mathematical system at all, axiomatic system, quite frankly, you can't prove consistency. It's unprovable within the system. You have to go outside the system to try to demonstrate it. Consistency, then, we just have to assume and have faith that our axiomatic system is consistent. Otherwise, it really would have no value. Now, completeness is another problem. You would like to think that if you have a meaningful statement that you can either prove that it's true or you can prove it's false. Well, that can't happen either. In any complicated axiomatic system, complicated enough to have, say, the natural numbers in it, then you would call it complete if you could prove any meaningful statement with a proof. But Kurt Gödel in the 1930s showed that can't happen. There are always meaningful statements that are unprovable in an axiomatic system. And by the way, this was a great crisis for mathematicians. They always assumed at the beginning of the 20th century, they always assumed that they could prove that their axiomatic system were consistent, and they assumed they were complete. Gödel came along in the early 1930s and showed neither one of those is true. You can't prove it's consistent. Well, you have to take a stronger system to prove one's is consistent. So it's like an infinite regret, and they're definitely not complete. So that's what mathematics is. Now, I'm going to talk a lot more about it going forward here in this video, but that's where you start. Now, you may say, well, then what good is it? Well, you use extensive definitions to assign a meaning to the undefined terms for a scientific model. These undefined and the defined terms are giving these extensive definitions. Like you say, a point. Well, what is a point? Well, you give it I'll tell you what it is. It's something, something you make with a pencil. What's a line? These are extensive definitions. And then that lets us create a math model, and that math model then is of some, what I'll call reality system, something we're trying to understand in reality, what you and I might call reality. And then the theorems that you're able to prove in the math system will tell us things about this reality. So the first axiomatic system was Euclidean geometry, and that was used by many mathematicians and scientists then to prove theorems that would tell us things about reality. Archimedes was one of the first really great scientists, and he applied a lot of the mathematical concepts to prove things about physical reality, and that's what's used in engineering and in science. And Archimedes was one of the first great scientists. And Euclid and Pythagoras, who came before Archimedes, proved a lot of mathematics. They created the what became known as Euclid's elements, the Euclidean geometry. And from that, then Archimedes, that and other things he did, was able to begin to prove a lot of scientific things. Now, here's something you need to know if you're thinking about becoming a mathematician. There are really an unlimited number of axiomatic systems. I won't say an infinite number, but an unlimited number. You can always create new ones, because you can always take arbitrary axioms, sets of axioms. A set of axioms with undefined terms is an axiomatic system, and there's no limit to them. Well, what sapiens have done, our ancestors, we simply have chosen certain ones that interested us. Usually it's because we thought they had an application to make a math model using a ostensive definition. Although later mathematicians began to study systems that just intrigued them. They thought they were beautiful. They didn't see any application for them. Now, a metaphor is this. Think of an axiomatic system as kind of like it would be an island out in an ocean. In other words, lots and lots of axiomatic systems. But most of them are submerged. Think of this ocean that has thousands and thousands of these islands submerged under the surface. When an island is submerged under the surface, that means we don't study it, we don't know anything about it. But a few of these islands rise above the surface and have been explored. Now, like I said, Euclidean geometry was one of the very first one that we began to study and explore. And then as time has gone on, new islands rise up and they're explored. And as time goes on, some of the islands that we were interested in, we abandon them and they kind of go out of sight again, sink below the surface. That's a metaphor. So now you can imagine that out of this ocean there are literally tens of thousands, perhaps millions of axiomatic systems. And we only choose to look at a few of them. So those are the ones that we consider that have risen above the ocean. And that's what math is all about. And our ancestors have created lots and lots and lots of axiomatic systems. There are literally hundreds of axiomatic systems, or islands if you want to think of that have been created and studied. Now, one of the things that is very interesting is that sometimes between two islands you can find a connection. And if you learn something on one island, that can tell you things about the other island and vice versa. Now, that really started happening, I would say, in the early 1800s. And the first one that I'm aware of that did this in a big way was a guy named Galois, Évariste Galois. And he created what was called a Galoisian connection between two different islands. And in so doing, he was able to take the information on one island and solve a very difficult problem on the other island that otherwise wasn't solvable. Men had for hundreds and hundreds of years tried to solve what is called the fifth degree equation using radicals. They could do it with the second degree, the third degree, and the fourth degree, and they just assumed they should be able to do it with the fifth degree. He was able to prove to them that that was impossible. And the way he did it, he took one island, he correlated it with a second island, and on the second island he could demonstrate that this was not possible, and then back to the first island, that showed it wasn't possible. So Évariste Galois really started modern math in a way. And that's not totally true, but he was the first one to find a connection, and today they call them Galoisian connections. Now, in the modern world today, in the we're in the early 21st century. I'm doing this on December 1 of 2019 is this video. Near the end of the 20th century, there were two islands that were very, very heavily studied. One was called elliptic equations or elliptic curves. I'm going to call them elliptic equations. And that was an island that had been thoroughly studied, actually started back in the time of the Greeks with Diophantine equations. And elliptic equations are an extremely important class of algebraic equations. This is algebra now we're talking about, number theory. And we knew lots about them. And mathematicians have made careers studying them. You can spend your entire life as a mathematician just studying what's on that island. Then there's another island that seemed totally unrelated called modular forms. And I won't tell you what that is, but it's another island where very important math concepts were studied. And then in the middle of the 20th century, somebody thought, there's a connection between these two islands. And there were two Japanese guys that actually discovered there might be a connection, and it became known then as their hypothesis that there was this connection. And as time went on, people thought, they could be right. This island of elliptic equations could be connected with this island of modular forms. Well, it turns out that there's a famous theorem that was discovered by a man named Fermat in the early 1600s, and he discovered a lot of theorems, and but he didn't give proofs of them, and so they would go into his book and they would create proofs, and there was one last theorem they couldn't prove that he claimed was true, and they call it Fermat's last theorem. Well, it turns out that if you could see this connection between these two islands, if you could prove there was a connection, a Galoisian connection, then you could prove Fermat's last theorem was true. And that was done by a great mathematician named Andrew Wiles in the latter, very near the end of the 20th century. And it's a fantastic story, and there's a wonderful book. If you're thinking of becoming a mathematician, this is a must-read book, Fermat's Enigma, by Simon Singh. I don't know how to pronounce his name, Simon Singh. This is a fantastic book because it goes all the way back into the history and comes forward and shows you a lot of the math that led up to this marvelous thing that, in fact, no other mathematicians thought it was provable. Nobody thought that you could find a Galoisian connection between these two islands. They thought it existed, but they didn't think anyone could prove it. And Andrew Wiles, over a period of 8 years, and this is after he had been very well educated in math, he was a mathematician at Princeton, he was able to prove it. It's an incredible story. Now, if you're thinking of becoming a mathematician, let me just tell you this. There are many math islands. I don't know how many, lots of them. First of all, you have the geometry. There's all kinds of geometries. There's Euclidean, Riemannian, projective, and many other kinds. And, of course, for hundreds, even thousands of years, Euclidean geometry was the only geometry we studied. We didn't even discover these other geometries existed. These islands were there until the 1800s. Riemann and Lobachevsky and others began to discover, hey, there's other geometries, there's other islands. And it turns out that there are relations between them, but they're different. And in fact, when you start applying to physics, you'll find out, for example, Newton applied to Euclidean geometry in the 1600s and created his model of physics, Newtonian mechanics. Then in the early 20th century, Einstein took a non-Euclidean geometry and he applied it to create relativity theory. So you have, and that turned out to be a better theory than Newton's theory. And I'll talk more about that in a moment. You have number systems. You have lots of different number systems, islands. There's a natural number system that everybody learns when they're elementary school. 1, 2, 3, 4, 5. Although there's all sorts of things about it that even today we don't understand. This natural number system has all sorts of meaningful statements that we think are true that we cannot prove. And there's many that we have proved that most people never heard of. Then the integers, which includes 0 and the negative numbers. Then the rational numbers, which includes all the fractions. Then the real numbers, which includes all the decimal expansions. And by the way, these are all embedded as you move along. And then the complex number system, which, by the way, going from rational to real wasn't done until the 1800s. And they actually did complex numbers heuristically before then. But for many years, complex numbers were considered unbelievable. They call them imaginary. And then came the hyperreals actually didn't come along until the mid-20th century. In 1966 is when the hyperreals came along. So these are things that have been developed over the years. Now, we have a lot of what are called algebraic systems. Many algebraic. We have what are called topological systems. We have things called finite vector spaces. This is called linear algebra. We have infinite vector spaces like Hilbert spaces and Banach spaces. We have groups, finite groups, infinite groups, fields, finite and infinite, and so on. Lie groups. The circle is a Lie group when it's interpreted right. E8 is considered one of the most interesting mathematical structures today. It's called an exceptional Lie group. And many more. Now, I'm telling you this because if you're thinking of becoming a mathematician, you're going to be studying many of these islands. And in fact, all of these are pretty much things I've taught over the years one way or another when I was teaching advanced math in my early years when I was a professor. Now, a question is reality a math system? Some people think, well, reality is really mathematics. In my opinion, the answer is no. Now, others disagree. I ask the question, is that just hubris? In other words, sapiens, we always think we know more than we do. We always think we're smarter than we are and have more wisdom than we have. A math system is simply a math model that is used to try to understand reality. You build a math model. As I mentioned earlier, Newton used Euclidean geometry in the 17th century. He also went beyond that. He used what's called calculus. Then came Einstein in the 20th century using a non-Euclidean geometry and more advanced math than Newton had access to. Now I'll say this, no math model is ever a perfect model. We have quantum theory models today. We have relativity models. These are two great models today for physics, quantum and relativity. And guess what? They contradict each other. Well, they can't both be right. And in fact, neither one of them is a complete model. We're trying to find a more complete model, and that's one of the challenges of physics today in 2019. We don't have it. We don't know. Math models are always incomplete, and that means there's meaningful statements that can't be proven true or false. So even if you got a model, there's statements within it you can't know if it's true or false. Let me give you an example. Is the Pythagorean theorem always true in a good math model in the world we live in? The Pythagorean theorem, that's the most famous theorem in geometry, probably in mathematics. A squared plus b squared equals c squared. I got a lot of videos on that where I talk about it. And is it true in the world we live in, on the surface of the earth, the surface of the sphere? And the answer is no, it's not even true there. You think, and I got a whole video on why the Pythagorean theorem is often not true. Now in mathematics, we've got something we call infinity. We've defined way back in the time of the Greeks. In fact, it really spooked the Greeks out pretty much when they discovered certain things about infinity. And I asked the question, is this the black hole of modern math? A black hole is something you go into, you really can't get out of. I personally kind of think it is. Most of our modern math systems today include the concept of infinity. I mean, you start studying infinity very, very early when you study math. And infinity is a very complicated thing. There are many infinities, by the way, many different sizes of infinity. That was discovered by the mathematician Cantor at the end of the 1800s. And what happens is this concept of infinity leads to all sorts of impossible situations in anything that's in the real world. And it gets more complicated. In modern set theory, it's an axiomatic system. We have something we call the axiom of choice. Now, the axiom of choice is absolutely necessary for many of the proofs in modern math models. In fact, if you study any of the modern math, you'll have like Tikhonov theorem in topology. You got to have axiom of choice. But it leads to theorems that are obviously impossible in the actual physical reality that we have. Unmeasurable sets being a good example of it. You can prove that you can take a sphere the size of a pea and make it the size of the sun. It's just crazy. But true, theoretically. Now, I personally think that we sapiens should be profoundly aware of our limitations and our ignorance. Chaos theory really alone should show us that. Chaos theory are math models where we know we can't predict the future. It shows profound limitations we have to make accurate predictions about reality, which means we don't, in a sense, understand it. The great Steve Wolfram points out that there are many math models that are irreducible in the sense that we can't predict their behavior in some simple way. We just have to let them play out over time. So, in fact, if you have a math model that is good for reality, chances are you can't predict anything. You just have to let it play out. Now, what you try to do, of course, is you try to accelerate the model on a computer, and you can do this to some degree and predict the future then by changing the time frame, but it's tricky. Now, I personally believe, and this is on other videos, that our best current scientific model is one that William Tiller's proposed. Dr. William Tiller, brilliant, brilliant man. I talk about it in other videos. But in his model, there's a non-physical component to reality, and I happen to believe in that. I don't believe that the physical world is all there is. I think there's a non-physical world, and that's where all sorts of things happen. Tiller talks about it in great length in his wonderful, go to his website, tiller.org, and he had lots of white papers and stuff. I believe that reality that we live in is actually much, much more complicated than any of our current scientific models. And I don't think we understand reality very much at all. I think Tiller comes the closest at this point in time, 2019. I think today we're sort of like where sapiens were, our ancestors in the 18th century. They were vaguely aware of electricity and magnetism, but they had no idea how it worked, what they could do with it, no idea of what was going to happen with the technology of the next 200 years. Nobody in 1750 or even in 1819 could predict where we were in 2019, 2 centuries later. No idea. Nobody then had any idea how it worked. We didn't even begin to understand it till the mid-1800s with Faraday's experiments. Then came Maxwell's equations. Then came quantum theory in the early 20th century. And nobody could see how this was going to transpire. And I think we are just as ignorant today as our ancestors were then. I think there's so much we don't understand and know. And so this is my idea of what math is all about. I'm going to talk on other videos about this concept of infinity, what I think might be the black hole of modern math, who knows, and things like that. So this was Craig Hane, Dr. Dell, and if you're interested in math, and particularly if you're thinking of becoming a mathematician, read the book I just told you about and have a great and wonderful life. See you on another video.